I am Dr. Anna Grinath, and my lab is the Biology Learning and Teaching Research Lab. And so for some background for us and the things that we think about in the lab, as a community, scientists share specialized ways of talking, writing, and representing phenomena. We engage in specialized practices like making observations, developing and using models, planning and carrying out investigations, analyzing and interpreting data, constructing explanations. And as part of each of these practices, scientists engage in argumentation. We engage in argumentation to make sense of those observations, to revise our initial models, to negotiate an appropriate experimental design, to scrutinize how data were analyzed or interpreted, and to evaluate alternative explanations. And so we might say that argumentation is at the heart of science. And scientists understand that any scientific claim, whether that's an idea about investigation design or interpretation of data or models or explanations, any of these claims are an assertion to be scrutinized and held accountable. And so we can think about this as argumentation being this social practice of science where all ideas are generated and held accountable by critique from the scientific community at some level. Because construction without appropriate critique would not result in science. And so scientists understand that what we know is only accepted in light of the practices and processes deployed to construct, critique, and revise that knowledge. And so this visual here is showing us that our conceptual structures, our concepts, and the knowledge, the actual knowledge, needs to be held and attended to at the same level as well as those epistemic practices, which are used when developing and evaluating scientific knowledge, and the social processes that shape how knowledge is represented and argued. However, commonly, our students come to understand scientific knowledge as just a collection of facts about the world because we tend to mostly privilege that focus on the conceptual structures. And this misunderstanding can affect students' ability to learn and use scientific ideas effectively. And so, if we hope for our students to have a deep understanding of both scientific knowledge and how it's generated, students need to learn how to play the roles of both constructor and critiquer. And in undergraduate biology education, we need to think about how to attend equally to the conceptual structures as well as those epistemic practices and social processes. And when we attend to all three of these, we're not devaluing the content. And here's a little bit of research to make my point. There's an instructional framework called argument-driven inquiry, which is some of the first research that I did. And this is called a practice-based approach to science learning because throughout this H-stage framework, students engage in all of the practices of science as defined by the National Research Council. And so we did a study where we were looking at biology classes in 2 different high schools. And in those high schools, they tracked students into honors and general level courses. We looked at a school that only engaged students in a narrow range of practices, your more traditional type lab settings. And we looked at a school that was using the argument-driven inquiry, or ADI, instructional strategy to engage students in a broad range of practices. And so after that year of learning, we gave the students 3 different types of assessments, one on concepts, one on scientific writing, which got to writing scientific arguments, and one in an investigation design and performance task. And so these graphs are showing us the scores at the beginning of the school year to the end. And then the dotted lines are the students that were engaged in a broad range through argument-driven inquiry, while students with the solid lines were engaged in a more narrow range of practices. So here we see that on that content knowledge test, all students did make significant learning gains, but the students engaged in a broad range of practices had a larger effect size. That is what the D is indicating. And when we look at the performance task, all students engaged in the broad range of practices made significant learning gains on the performance task, but only the students in the honors section at the other school made gains. And then lastly, when we look at the scores on the writing assessment, only the students that were engaged in a broad range of practices made significant learning gains on that writing task. And so my point here is to emphasize that when we engage students in a broad range of practices, they are learning content for sure, and they're also learning to participate in more of the practices of science. And so this brings me to the driving question that we think about in our lab. How does authentic engagement in the practices and discourses of science shape student development as a scientist? And by development as a scientist, I'm thinking about all three of these pieces, both conceptually, engagement in epistemic practices, as well as those social processes. And then another question is how development in those three areas then affect the science identity of our students. And so thinking about coupling content with practices is a new challenge for us to think about in undergraduate biology classrooms, and I found it productive to draw on a set of instructional sequences that are called ambitious teaching practices. And so these start with first selecting a core biological phenomena that we can investigate to learn still a bunch of our different topics that we need to learn, but it's in the context of an overarching phenomena. We need to elicit students' initial ideas and the productive ways that they come into our classroom already thinking about the world. Then we also need to engage our students in scientific practices to help them test those ideas that they hold. And then lastly, press them for evidence-based explanation, drawing from the evidence they collected while engaging in scientific practices. And I found these instructional sequences particularly fruitful because they are discursively rich. And so they provide opportunities for argumentation, accomplishing the goal of attending to the integration of content and epistemic practices and social processes within scientific activity. And so an overview of the research happening in this lab is taking place in biology learning contexts that have opportunities for ambitious science teaching practices, but often part of my research is to create such contexts. So I think a lot about instructional and assessment design, using design-based research to systematically design and test contexts that should theoretically support ambitious teaching. And within those contexts, I conduct qualitative and quantitative research to study how those contexts support student learning, student uptake of practices, and students' development of their scientific identity. And then the last piece is to also study how to design professional development to support the teachers teaching in those contexts and how teachers learn to teach with ambitious teaching practices. And so I'm going to spend the rest of my time here just highlighting a few different studies that are current and ongoing research in the lab. And so the first, and you'll see the diagram in the top right here, shows that overview and highlights kind of the area of the research that this project focuses on. And so with my colleague, Dr. Seth Jones at Middle Tennessee State University, we have thought a lot about developing a framework to help guide us in attending equally to those three pieces that are so important. And I'm not going to walk you through this entire framework, but I'm just going to show you that thinking about how to couple these things together is a problem that we need to solve and think carefully about. And so in our work, we found that it's been really helpful for us to first think about which epistemic practices we want to engage in, and then think about the biological phenomena that will allow for students to engage in those epistemic practices, as well as what biology content they're going to learn. And then it proceeds on through the rest of that diagram. And so using this diagram, we have developed some lessons along with some people doing this work with us that you see on the top there. And so one of these lessons we refer to as the sponge filter feeding lesson. And we're thinking about how the epistemic practices is thinking carefully about how to turn a qualitative entity into a quantitative measurement. And so think carefully about measurement and then support students to think about structuring those measurements as distribution and then allowing students to actually invent their own ways of measuring features of that distribution, otherwise known as statistics, and then developing scientific arguments to support guiding questions. And so this is ongoing research understanding how this lesson, guided by the framework I was showing you, supports students learning to engage both in practices and learn content. Another context that I designed first to allow for opportunities for argumentation happens in an undergraduate biology lab. And you can see the pieces of the ambitious teaching practices highlighted here. And so the lab followed the sequence of first eliciting ideas, then engaging in practices and pressing for evidence-based explanations, where there would be opportunities for argumentation within each of those. And then I also needed to think carefully about how to support the teaching assistants who were teaching those labs, which I'm not going to spend much time on, but know that was something that was thought about. And I'll just share one little question with you that we looked at, just in terms of eliciting students' initial ideas, we were wondering, how do TAs elicit and respond to the initial hypotheses students bring up in class? An important thing to know about this question is that when we think about talk, we can think about it in sequences, where if I ask you a question, that's the first turn. If you respond, that would be the second turn. And then if I say something again, that would be the third turn. And so across all of these discussions, we found that no matter what the first turn was, no matter what type of question the TA asked, that didn't tend to elicit really rigorous student ideas or explanations. However, that third turn, if I ask you a question and you give me a response, what I say to you in response has dramatic potential to elevate the quality of the ideas that are being put forth in that classroom. And so one little takeaway is that that third turn we really need to think about in terms of the rigor in our classrooms. And I'm going to spend my last minute highlighting a few more studies. So that relates to research that Miranda Coons and Ruth McNeil have both done in the lab, looking at how the lab, how that course sequence affected students' motivation. And Ruth seems to be finding that motivation is really, really affected by how what TAs say in that third turn. And so look for more information on that coming soon. We also need to think carefully about how we support TAs. And so Alyssa Freeman in the lab is looking at how, when we design instructional supports, how do TAs engage with those? Then how do they enact the lab? And then do we observe epistemic talk? And that's in collaboration with some other folks at MTSU, and she's going to tell us more about that at her proposal seminar. And then another project is looking at actual scientific communities of practice that we didn't have to design and asking similar questions in those contexts. And Gabby Jablonski in the lab is thinking about how engaging in argumentation affects biological identity and disciplinary authority. And last but not least, Ashley Rasmussen, who's a DA student in the lab, is thinking about a different practice in terms of how incorporating drawing into our courses can help us learn how to observe and pose questions through illustration. And you can hear more about that at her proposal seminar on October 29th. Thank you.